There's a kind of continuity going on here that every once in a while I like to be a bit retrospective, bring back past learnings. There was a time in this course where I was pleased that I could predict the velocity in the future, that the velocity is equal to the initial velocity plus the acceleration times time. And I also was pleased that I could predict the position in the future because x is equal to x naught plus v0t plus 1/2 a t squared. But both of these so-called kinematic relationships require that I know the acceleration, which is the rate of change of velocity of an object. But once you establish that, in every physics class that there ever was, once you do all of those kinematics things, the next question is, why do things accelerate in the first place? What is the cause of acceleration? And you already know this quite well, because along comes Isaac Newton with the first, the second, and the third law. Primarily, the second law tells us that in our universe, we can describe natural constraints or conditions that we call forces, and a force is the cause of acceleration. Free fall acceleration is caused by gravity. The acceleration of a crate along the floor could be caused by someone pushing against friction. The acceleration is caused by forces impressed thereon, and then we do a bit of energy and a bit of momentum. And now we find ourselves again talking about acceleration, but not translational acceleration, not acceleration in a straight line, but instead the acceleration of rotating objects. Because I already decided that I can describe the rotation of an object in terms of an angle, and that there's a rate of change of that angular position that I call angular velocity. And there's a change in angular velocity that I call angular acceleration. And sure enough, I've got an equation that says omega is equal to omega naught plus alpha t. It's the same equation again. Instead of b is equal to v naught plus a times t, it's omega is equal to omega naught plus alpha times t. It's the rotational analog. It's the same thing. So I find myself in the same place asking, if an object is rotating, but its rotation is increasing, that is, it has a positive angular acceleration, or if a thing is rotating and it's slowing down in its rotation, that is a negative angular acceleration, what's the cause of the angular acceleration? And everybody knows the answer. It's the same answer as it was before: force. The best example of a rotating object that I have here is the door. A door does not translate. When I engage with the door, it doesn't fly across the hallway or head down the hallway, thusly. It rotates about an axis of rotation that is the hinges of the door. I exert a force. Everybody understands. Everybody knows how to use a door. But a thing that you're aware of, but not maybe conscious of in the sense of understanding the nature of your universe, is that when you push on the door, you want to push on, in this case, the hinges on the right. I push on the left side of the door because that is how I get the largest angular acceleration. I've got a certain amount of Shidley force, and I apply it to the door, and the door opens. You would question the sanity of an individual if you came by and saw them pushing here at the right-hand side of the door. The door won't open. Well, of course the door won't open. You can't open a door by pushing on its hinges. It turns out there's a continuum to this. If I push in the middle of the door, I find it's difficult to get an angular acceleration. But if I push as far away from the hinges as possible, I get a large angular acceleration. So in terms of what is the cause of angular acceleration, it is absolutely force, no question about it. But there's also an aspect of how you apply the force. And that's what today's discussion is about. There we go. Newton's second law told me F is equal to ma, that the acceleration that I get is the force, and the constant of proportionality is the mass. The mass of an object represents its resistance to acceleration. A thing with a large mass requires a lot of force to accelerate. A thing with a small mass requires very little force to accelerate. That's F equals ma just as a qualitative idea. If a thing is massive, it's hard to accelerate. Mass, by our definition, using the official language of our course, mass is the measure of an object's inertia. So a certain number of kilograms that I measure on a pan balance or some other technique that I use, a certain number of kilograms describes the resistance to acceleration. There's another kind of inertia. And if you don't mind, I'm going to have you help me out with this demonstration. I have a demonstration apparatus here that I'm going to allow to be passed around the room as I talk. I'll be doing my thing, so be careful not to hit your neighbor in the face with the apparatus. We're going to demonstrate this. Here are these two rods, and they look very much identical. They're not identical. There's some wear and whatnot. They're a little bit smashed up. But I'll tell you the thing that's true about these two rods that I hold in my hand. They have equal masses. Now, you can't tell that that's true by looking at them. Looking at them does not measure their inertia. The way I'll measure their inertia is by accelerating them. So I'll take them and just go back and forth like this, in a straight line, linear acceleration. And when I accelerate them, I find that it takes as much effort to accelerate this one as it does to accelerate this one. They take the same effort to accelerate. Therefore, they have the same mass. Now, I didn't actually put them on a pan balance and measure them, but I can get the idea. I can feel it. The experience is extraordinarily different when I rotate them, like this. So I want you to be the first one to testify, grab hold of them in the middle as I did, and go back and forth like this, and they're the same mass, aren't they? Yeah. Now, twist them. Ooh. And you immediately try to process and figure out why. Don't worry about it. At the end, we're going to come back to it. We're going to explain why. So if you wouldn't mind, pass the apparatus along. When the apparatus comes to you, if you don't feel like messing with it, you can hand it on to the next person. Just let it make its way around the room. Every object that I choose to rotate has a certain natural resistance to rotation, not inertia. Rotational inertia. Just like I said, not velocity, angular velocity. Everything seems to have its rotational analog in this situation. Not inertia, but rotational inertia, which is easy to find because rotational inertia is an object's resistance to angular acceleration. Rotational inertia is the measure of an object's resistance to angular acceleration. See how these definitions are so similar. The rotational inertia depends not only on the mass, but also how far the mass is from the axis of rotation. Now, in order to give you an equation for calculating moment of inertia, an equation, I would need to use calculus. But I'm not going to let that stop me from talking about it because the moment of inertia, for which I'll use the symbol I, the moment of inertia I, not M, M is inertia, mass. The moment of inertia I is proportional to, that's not the first time we've seen that symbol. The moment of inertia of I is proportional to the mass of the thing. The mass matters. Yes, it's about mass. The mass of the thing. But multiplied by r squared. Now, usually when we see r appear in our math or even in our science, we think of radius, that r is the radius of some things. And very often that's true. But r really is a position, even if it's a radius. It's a distance in space. It's measured in meters. So this quantity, the moment of inertia, would have to have units of kilogram meters squared. But that's not the interesting thing. The interesting thing is that the moment of inertia describes how an object resists rotation, which is different for every object, because every object has a different mass, but more importantly, the mass is distributed differently. I say more importantly, and so does the equation. Because the r in the equation is squared, the way I interpret that is that the r is more important than the mass. If you square a quantity, gives that quantity more oomph in the calculation and means it's more important to the ultimate overall quantity. Now, if we wanted to write an equation for the moment of inertia, I equals, the equation would depend on the object that you're talking about. For example, I have here a hoop and a disc that I'm going to demonstrate with in just a moment. I have a hoop and a disc. They have different moments of inertia. Their moment of inertia equations, which I happen to know by heart because I do a lot of physics, their moment of inertia equations both have mr squared in, but each one has a different fraction in front of it. It happens to be true that the moment of inertia of this thing is equal to, the hoop, is equal to mr squared. But the moment of inertia of this one is equal to 1/2 mr squared. So there's always an mr squared in a moment of inertia. For example, the moment of inertia of a sphere is 2/5 mr squared. There's always some sort of weird fraction in front. We're not going to concern ourselves with the fraction. We're going to concern ourselves with the definition of moment of inertia in terms of how much mass it has, sure, but also how the mass is distributed relative to the axis about which it rotates. For example, here I have a very simple idea, a pencil. The pencil can be rotated a bunch of different ways. Here's 3 examples. In the first case, the pencil is being rotated around its long axis. In the second, the pencil is being rotated around an axis that goes roughly through the middle of the pencil. And in the third instance, the pencil is being swung around an axis that's over here on the right-hand side nearest the eraser. In each one of these instances, it's the same pencil, so it has the same mass. The masses aren't different. What's different about each one of these situations is how far the mass is from the axis of rotation. In the first case, the top case here, where the pencil is being whirled around its long axis, do you see that every little bit of mass of the pencil is very, very close to the axis of rotation? Very, very close, because the pencil is very slim, so to speak. As a result, the r is rather small, and I'm going to say that this pencil has a low moment of inertia, because the mass is not very far from the axis of rotation. Here, the mass, certainly there is some mass in the middle instance here. There's some mass that is close to the axis of rotation, that's for sure. But there's a lot of mass far away to the right, and there's a lot of mass far away to the left. And when you do the actual calculus to work it out, the moment of inertia here is sort of medium. In the third instance here, the moment of inertia is quite high, and hopefully you can see. While it's true that some of the mass, here on the right-hand side, nearest the eraser, is close to the axis of rotation, much of the mass is very far away. And since r is squared in the equation, when the mass gets further and further away, the moment of inertia gets larger and larger and larger. So now this apparatus of the 2 rods has made its way around the room. And what you've discovered, as you messed around with it, that while it's true that they have the same mass, like in each one of these instances, the pencil has the same mass. While they have the same mass, when you turn them, this one is stupid easy to turn. And this one is very difficult to turn. This has a very low rotational inertia. It's easy to rotate. This one has a very high rotational inertia. It is difficult to rotate. Now that you've handled this and you've seen the demonstration, can you explain why there's a difference between the two when they have the same mass? What's the secret? What's the trick? You think it's an air resistance thing? In the case of the rod, well, let me say it this way. You see there's a pipe, and you're right, like air gets in the end, because this end of the pipe seems sort of hollow. The reason why, both of these pipes have 2 slugs in, 2 masses inside each one of them. In the case of the one that's easy to turn, the 2 slugs are right here where I have hold of it. The mass is all at the axis of rotation. And because the mass is close to the axis, it's easy to turn. This one is constructed of identically the same things, a pipe and 2 masses. But in this one, the masses are far out here at the end, far away from the axis of rotation. And because the position of the mass matters more than the mass itself, this one has a larger moment of inertia, and this one has a small moment of inertia. The moment of inertia is going to make it possible for me to, theoretically, calculate how much acceleration I expect to get in any physical situation. The moment of inertia affects the dynamics of the situation. I have a ruler here, and I'm going to use the ruler to prop up this end of the, let's see if I can do it effectively. I've used the ruler to prop up the end of the table. Now the table's like a hill. And I have these two discs. They have the same radius. Now you see, the hoop is made of steel, and the disc is made of wood. I assure you, they have the same mass. Now there's a little bit of inside baseball behind that, because it would turn out that if we worked out the physics of this in detail, the masses would cancel. You know that happens sometimes. You do a calculation and the masses cancel. That's a thing of physics. And it would happen here. But I promise you anyway, for your own thinking, their masses are nearly identical. But the mass is distributed differently, and so they have different moments of inertia. I wonder if you can guess, if I start them here and have a race, will they reach the far end of the table at the same time, or will one of them win? You think that the hoop is going to win. The metal hoop is going to win. What gives you that suspicion?
I think the wood would win. Yeah. I think the metal's going to win.
Well, hang on a second. Let's get some physics, see if we can get some physics reasoning. Oh, so you're guessing. All right, so give me a little physics insight. You see, you disagree. You think it's got to be the disc.
I think it's because it's kind of like the metal poles.
So on the disc, the weight is some of the mass is close to the axis of rotation. So that would mean that this disc is easier to rotate. Oh shoot, right? Because in order to roll to the end of the table, in order to roll, you have to rotate. So if the distribution of mass in the disc gives it a lower moment of inertia than the hoop, and you got to rotate to roll, it's almost like a catchphrase. This is how I translate and rotate simultaneously and feel regret at saying things out loud. Which wins? Yeah. So I don't even have to do it, right? Because I've reasoned it out.
I think the other one,
the disc, how dramatic. The disc has a smaller moment of inertia and rotates more easily, therefore rolls more rapidly and has the larger angular acceleration. The action of a force to turn a thing is called torque. I think to some of us that might be a familiar term. For example, you may have heard that there's a device called a torque wrench. It's a specialized kind of tool that's designed to twist a bolt to a very specific tightness, because sometimes engineering applications require that. For example, the bolts that are used to bolt a car engine motor together are often tightened to a very specific tightness using what is known as a torque wrench. Torque is a force acting at a distance, and the best example of that beyond my classroom door, which works quite well, is using a wrench to turn a thing. Here in the first instance on the left-hand side, we see a very common everyday situation. There is a bolt. The wrench has been fixed to the bolt, and the hand is being used to turn. But notice very specifically, the diagram has been drawn so that the force is sort of off at an angle. I might say that the wrench is being used sort of casually to turn the thing. This results in a torque because in this leftmost example, I suspect that unless this is already very, very tight or rusted in some way, that this force may very well be applied in such a way that it would cause it to turn. But if this angle were to get more extreme so that it was horizontal, I think we know for a fact that if I place a wrench on a bolt and then pull away from the bolt, the wrench just comes off. It doesn't turn anything. To turn effectively, the force should be applied perpendicularly to the distance. The best application of the force. It applies to the door as well. If I go over here to the door and I go to open it, but instead of pushing perpendicular to the door, I push it at an odd angle, I find the door difficult to turn. We all know instinctively that you get the best motion out of the door by pushing on the door perpendicular to the line drawn from the axis of rotation to the point at which the force is applied. This is torque. I think we also know that the further you go, the greater torque that you get. This diagram here on the right shows a pipe has been fitted onto the end of the wrench. This is a common strategy used by mechanics. You put a wrench on a nut and it won't budge because it's rusted or it's super tight or whatever. You can take a pipe and put it over the wrench to extend the distance between where you exert the force and the axis of rotation, and you can exert enough force to cause rotation. This is sometimes called a breaker bar because it's used to break a difficult nut free. This all becomes clear in my definition of torque. Here's torque, for which I use the lowercase Greek letter tau. That is not a wee t, it is the Greek letter tau. It's a stubby t with sort of a tilde on the top of it. You can invent your own style of drawing the torque, which is tau. What does it depend on? Well, it's to be hoped that throughout the course of our physics, we'll learn to read equations well. What does torque depend on? Force. F is the force. It takes force to turn a thing. But I also learned, horsing around with the door, that if I apply the force close to the axis, I don't get a lot of angular, especially if the door's latched. If I exert the force close to the axis, it's hard to turn the door. But if I exert the force far away from the axis, it's easy to turn the door. The torque also depends on L, where L is the distance from the axis of rotation to the point at which the force is applied. L is this distance from the axis of rotation to the point at which the force is applied. But it also depends on the sine of the angle. And the reason why is that if you exert a force at an angle, you're wasting some of the force. Some of this force in the left-hand diagram that's sort of, if you look at in terms of components, maybe I'll just draw these components on here. This force has a component that is perpendicular. It's a force that's good for turning. It has another component that is radially away. That component's good for pulling the wrench off the nut. That doesn't do any good at all. In order to get a good turning force, in order to get a good torque, you want it to be perpendicular. So you want this component that is perpendicular. If this angle between the applied force and in my diagram here, the horizontal, is theta, then the component I want is the opposite component, the sine theta component. This equation is torque by definition. Torque by definition is the force times the length times the sine of the angle. Notice, sine of theta doesn't have any units. Sine of theta is dimensionless. Force measured in newtons, length measured in meters, means that the torque has units of Newton meters. Torque has units of Newton meters. And if you're a good student, take good notes, you say, yes, sir, Newton meters. But if you're really paying attention as a student of physics, that's a little strange. Because it turns out in a weird way that we don't need to worry about, it's not going to affect anybody's test grade. A Newton meter has another name. It's also called a joule. We never ever say joules of torque, though. Torque is always described as Newton meters in SI units. It's also true, it's described as pound-feet in European, or imperial units. But we'll stay metric if you don't mind. Torque measured in Newton meters. Now put the whole thing together. Because I now understand that objects have a resistance to rotational motion called the rotational inertia. We know that a force can cause rotation as a torque. I know. Sometimes it seems like you're in physics class and time stops, but the first thing that I said was, back in the day, I wanted to know what the acceleration was, so Isaac Newton told me that the force is equal to the mass times the acceleration. You can find the acceleration if you can work out what the forces are. Now what I'm going to do is just create a rotational analog of that equation. Newton told me that the sum of the forces equal mass times acceleration. We're physics students, so we see that. It's very familiar. Sum of the forces equal mass times acceleration, of course. If you can work out the net force, the acceleration will be in proportion to the mass, because the mass is the measure of the inertia, and the inertia describes the resistance to acceleration. Look what I've done. I have taken the force and replaced it with its rotational analog, the torque. I've taken the mass and replaced it with its rotational analog, the rotational inertia. Inertia for inertia, force for force. And I've taken the acceleration and replaced it with its rotational analog, the angular acceleration. I know those equations sort of aesthetically look very different because they include very different symbols, but they are identically the same equation. One describes the translational physics. If I can work out the forces, I can find out the translational acceleration. The second equation works out the rotational physics. If I can understand the net torque that acts on a system, I can predict what the angular acceleration is. And if I know what the angular acceleration is, then I can omega is equal to omega naught plus alpha t, all I like. Now, when this moment happened earlier in our course, and the slide said only sigma f equals ma, the very next question that I asked is what would happen if the sum of the forces was equal to 0? What if the net force is equal to 0? And that can easily happen. If an object experiences 10 newtons to the right and 10 newtons to the left, because force is a vector, those forces are equal and opposite, they add to 0. When the net force is equal to 0, the acceleration is 0, and we call that equilibrium. Equilibrium is the state of motion where the net force is equal to 0. Well, now I'll ask the same question. What happens when the net torque is equal to 0? What happens when sigma tau is equal to 0? When all of the clockwise torques that would rotate the system in a clockwise direction, say 10 Newton meters of clockwise torque, are met with 10 Newton meters of counterclockwise torque, such that the sum of the torques, the total torque, is equal to 0. Well, then the angular acceleration would be equal to 0. I should call that equilibrium. But I'll call it rotational equilibrium, when the net torque is equal to 0. Here are two kids on a seesaw. And I don't know how much you've messed around on playgrounds with this sort of thing. Hopefully this is a relatable childhood experience. But here we have two kids sitting on a seesaw. One, sitting here on the right, is a particular distance to the pivot that I call D2. Distance 2, as you can see here on the diagram. Their friend is on the other side of the pivot at a distance that I call D1. Further away, D1, clearly you can see that D1 and D2 are not in fact equal to each other. Each one of these kids on this seesaw exerts a force. And since they're sitting at locations different than the axis of rotation, which is the pivot point, they exert torques. But the angular acceleration is equal to 0. It's not just a static picture. They're sitting there and not rotating. They're stationary. Probably anybody who came along and witnessed this would say that they were balanced. They're balanced because the angular acceleration is equal to 0, which means the net torque is equal to 0, which means the torque exerted by the girl on the left, which I can calculate as the force that she exerts, which most certainly is her weight, yes? Most certainly is her weight, multiplied by the distance to the axis of rotation, which is the pivot. So her torque is F1 D1. Because the weight is perpendicular to the distance, I didn't have to mess around with any sine theta nonsense. The weight is perpendicular to the distance, so it's easy to calculate the torque. It's the force times the distance. In rotational equilibrium, that has to be equal to the force exerted on the right and the distance between where that force is exerted and the pivot, which is the axis of rotation. So despite the fact that these two children, I suppose, on the teeter-totter, although if you're an adult, be youthful in spirit. These two here on the teeter-totter, despite exerting different forces, are in rotational equilibrium, which would allow me to solve for any one of the distances or any one of the forces. Notice, since the girl on the left is further from the pivot than the boy on the right, I can conclude that the force F2, which is presumably the weight of the boy, is larger than F1, presumably the weight of the girl on the left. This is how we create a scale and compare the weights of two things, sliding them this way and that. I know today we're very familiar with using digital pan balances. You just turn the thing on and throw a mass on it. It tells you how much mass it is. But of course, old school, if you will, masses could be slid to the left and to the right until a rotational equilibrium was found, and that rotational equilibrium allows us to solve for the unknown. By way of example, consider this balance here, very much like the example we just looked at. But here I only know one of the forces and I don't know the other, and the only thing I can assure you of is that it is in rotational equilibrium. That is, the angular acceleration is equal to 0, which means the sum of all of the torques is equal to 0. There are two torques. Here I have a torque exerted by a 12 Newton force that, if left to its own devices, would rotate the system in a counterclockwise fashion. And I have a mystery force over here that would rotate the system in a clockwise fashion. They are counter torques. They could add up to 0. That is, they could be equal to each other and creating an opposite influence. So writing this as an equation, I'll take the force exerted by the 12 Newton force here, which will be 12 newtons, and multiply by its distance to the pivot. Well, I don't have any units or tick marks on this. I just have sort of blind tick marks. But it doesn't matter if it's centimeters or meters or furlongs or light years. It doesn't matter. I've got 3 of them. 1, 2, 3. So the torque on the left-hand side of the pivot, the torque that would be counterclockwise, is 12 times 3. That would be the torque, a force multiplied by a distance. On the right-hand side of the pivot, we have a mystery force, I don't know what it is, multiplied by, as it happens, a greater distance. Count the tick marks. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it would be that force times 9. And based on the rotational equilibrium, I can solve for the unknown force. Simply enough, 9 divided by 3 is 3. 12 divided by 3 is 4 newtons of force. I'm able to determine the unknown force based on the notion of rotational equilibrium, where not the forces are not equal. One force is 12 newtons, the other one is 4 newtons. The forces are not equal. It is the torques which are equal and opposite in rotational equilibrium.